Ever wonder how you build a system that is literally not allowed to fail? I mean, imagine the mind-boggling complexity of designing a massive, fail-proof infrastructure. Think of a national railway network. You're dealing with thousands of tons of metal hurtling along at high speeds. You've got super complex digital communications, unforgiving environments, all while being responsible for protecting human lives. It sounds kind of impossible, right? Well, welcome to today's Explainer. We're going to dive right in and unpack exactly how engineers manage to tame all of this chaos.
To actually achieve the impossible here, engineers rely on a master method. It's called application design. Now, this isn't just about drawing up a few nice schematics. It's the absolute fundamental blueprint for managing complexity, ensuring safety, and building systems that are going to endure for decades.
Here's our quick roadmap for today. First, we'll talk about taming complex systems. Second, establishing the design baseline. Third, selecting system architecture. And finally, interdisciplinary integration. Let's jump right into it.
Okay, part 1, taming complex systems.
So what exactly is application design? Simply put, it's the process of taking a massive overall system and breaking it down into manageable subsystems. But here is the real secret sauce. You have to identify exactly how those subsystems interact, because just breaking things apart isn't going to cut it. For example, a train detection system is totally useless if it can't communicate with the physical track signals. The magic, and honestly the danger, is always found in those interfaces.
Moving on to part 2, establishing the design baseline.
You can think of the design baseline as the definitive single source of truth for the entire project. It's a highly controlled set of documents and drawings that have to be rigorously checked before any actual implementation begins. Now, you might be wondering, why is this so incredibly formal? Well, because before anyone cuts a single piece of metal or writes a line of code, you need absolute assurance that the design can actually be built and that it meets every single safety requirement.
And the stakes? They are astronomically high. There's a phrase engineers use, 40 years system lifetime of regret if you get it wrong. Skipping these rigorous baseline checks doesn't just cause a temporary headache on the construction site. Designing for dependability from the start is so much cheaper and way more effective than trying to retrofit it later. If your baseline is wrong, you're looking at catastrophic functional and financial consequences over the whole life of the system. You are literally building in decades of failure. No pressure, right?
All right, part 3, selecting system architecture.
When you're building something like a digital traffic control system, you're looking at a seriously complex web. It requires a highly strategic framework. Imagine the distinct layers involved. You've got central traffic management systems sitting at the top, routing down through complex logic processors, all the way down to physical trackside equipment like the actual mechanical points and signals. Selecting the right architecture for a multi-layered system like this is an intensely rigorous process. To figure this out, engineers filter their architectural choices through a very strict 3-step criteria, because let's be real, you can't just pick the newest or flashiest tech off the shelf. First, the architecture has to meet strict customer standards and safety rules. Second, it actually has to survive the operating environment. And third, it has to make solid economic sense when you look at whole life costs. So it's a constant, tricky balancing act between rules, physical reality, and money.
Let's zoom in on that second point for a second, the operating environment. This architecture has to survive harsh, totally unforgiving realities. A pristine lab environment is one thing, but out in the real world, we're talking about severe electromagnetic interference from high-voltage train lines, absolute temperature extremes baking the electronics, flooded tracks ruining circuits, and the massive, violent physical vibration of heavy freight trains roaring by. Then, of course, there's the money aspect. When selecting architecture, engineers are always comparing the initial upfront capital cost against the lifetime operations and maintenance costs. And here is a huge takeaway. Operations and maintenance almost always exceed the capital cost over a system's lifetime. Think about it. A cheap component that constantly requires a technician to walk out onto a live, dangerous railway track to fix it, that's actually massively expensive, both in terms of ongoing financial cost and the safety risks involved.
Which brings us to our final section, part 4, interdisciplinary integration.
This is where things get really interesting. Enter Inter-Disciplinary Checks, or IDCs for short. You can think of IDCs as the ultimate clash detection system. They are mandatory reviews designed to make sure that the digital and mechanical dreams of the control engineers don't turn into physical nightmares when they interact with the civil engineers or the track layers. Because at the end of the day, the railway is one holistic system. Every single part has to work together perfectly.
Let's ground this theory in some reality. Say you're designing the train detection system. Well, you absolutely must talk to the track engineers. Why? Because if the track they lay is unstable, your high-tech detection system is going to fail. If you're handling digital comms, you have to coordinate with civil engineers, or else a physical tunnel they build might completely block your data signals. And if you're installing sensitive electronic signaling, you've got to work closely with the electrification team. Otherwise, their high-voltage power lines are going to cause massive electromagnetic interference.
Just to give you a really tangible example, if the physical track shifts, the digital system completely goes blind. Think about that. You could have the most advanced, ridiculously expensive, highly redundant control architecture in the entire world, and it is completely useless if the physical steel rails it's monitoring aren't stable. This right here is exactly why working in silos always fails, and why those interdisciplinary checks are totally non-negotiable.
So to bring it all together, what does a successfully integrated, baseline checked architecture actually look like? Well, it defines strict performance and capacity budgets. It makes sure technical interfaces perfectly align with organizational ones. Every single feature is directly traceable back to the original safety requirements. And above all, it builds in fault tolerance. So when a component inevitably wears out or fails, the whole system degrades safely rather than just collapsing.
And that is how a rigid blueprint transforms into a living, breathing, and above all, safe reality. Through this incredibly structured, almost obsessive process of application design, engineers take overwhelming complexity, break it down into interacting subsystems, lock it in with a definitive baseline, pick resilient architectures, and force cross-discipline integration. That's the secret to the incredibly safe infrastructure that we all rely on every single day.
So I want to leave you with a thought. We've just seen how strict design baselines, careful architecture selection, and rigorous interdisciplinary checks keep massive, chaotic railway networks from failing. So how might you apply these exact same systems engineering methodologies to tame the complex, chaotic systems in your own personal or professional life? Thanks for joining me on this explainer. I hope it gave you a powerful new blueprint for thinking about complexity.